Hey Fizz Kids, Mr. C here, and we're going to kick off with our first video about momentum. And we're basically just going to talk about what is this thing that I call momentum. So, what is momentum? Momentum is just the product of mass and velocity. So we symbolize it with this cool letter P here. So P is just equal to mv, and its units, because I love units, so you have to know this, are kilogram meters per second. Momentum, just like all my other favorite quantities in physics, well, other than energy, but of the other ones, momentum is a vector, which means that it has a magnitude and a direction. So make sure that you take that into consideration whenever you're adding momentums together. Because remember, we can only add vectors that point in the same direction together. The way that we know the direction of the momentum vector is it's always in the same direction as velocity. So if velocity points north, so does the momentum vector. If we wanted to break it up into components, we know that the x component of momentum is just going to be equal to mass times the x component of velocity, and the y component of momentum is going to be mass times the y component of the velocity. We're going to talk more about two-dimensional momentum later on in the chapter. Right now, we're just going to kind of focus on 1D momentum. So, uh, how do we get momentum? How do we change momentum? Well, in order to change momentum, we need this thing called impulse. And impulse is stated with a J. So impulse is basically a force acting over some interval of time. And the way that we write it in physics is J is equal to the average force times the time that that force was applied. And we also know that this J is equal to our change in momentum, which is our final momentum minus our initial momentum. The units, so we're right over that. The units of impulse are a Newton second, which is the exact same thing as a kilogram meter per second. So impulse and momentum have the exact same units. Impulse, in this case, is a vector quantity as well, and it's going to point in the same direction as the average force. This equation up here is really good if, say, we have a constant force or a linear force or something like that, where we can use the average force. Or the average force is easy to find. However, a lot of times, average force is not easy to find, and maybe it's over a really, really short time interval. The way that we can actually find out impulse also is if we have a force versus time graph, so force on the y-axis and time on the x-axis, the area underneath our curve, so all of this right here, is actually going to be equal to our impulse, which also, as I mentioned earlier, is equal to our change in momentum. So the area under a force versus time graph is going to be the impulse. So let's look at this example. So we have a rubber ball that bounced on the ground, and this is a force versus time graph of our rubber ball. And we want to know two things. We want to know what is the impulse on the ball, and we want to know what the average force is. Well, in order to find the impulse, what we would do is we would actually look here and we'd say, well, we know that the impulse is equal to the area under the curve. So we know in this case that impulse is going to be equal to 1/2 times 0.008 seconds times 300 newtons, and that will give us what our impulse is. Part B is we want to know what is the average force on the ball. Well, we also know that that same impulse from above is going to be equal to our force times our change in time. So if we want to solve this for force, we know that force is equal to our impulse divided by delta t, or in this case, we would take that 1/2 times 0.008 times 300 newtons, all divided by 0.008, and we find that our average force in this case is going to be 150 newtons. Pretty cool. This is just walking us through the same thing. So I pretty much just told you now that impulse and momentum are linked together, that they're the same thing, but I haven't really told you why, or proved it to you, I guess. So let's say that we have some block that's moving with some initial velocity, and we act on it with a constant force over some time. So I push this block, and it moves, it's a constant force over some time, and now at the end of that time period, we have a final speed vf. Well, using kinematics, we know that our final velocity is going to be equal to our initial velocity plus acceleration times our change in time. We also know that in this case, a force is equal to mass times acceleration, or our acceleration is equal to force divided by mass. So we can go ahead and plug that into our acceleration, and we get that our final velocity is equal to our initial velocity plus the force divided by mass times delta t. And if we rearrange that, because we know that this quantity here is our impulse, we can actually find that force times our change in time is going to be equal to our mass times our final velocity minus our mass times our initial velocity. And this is what we call the impulse momentum theorem. So this is how, if we simplify this even further, we know that F times delta t is equal to PF minus PO, or F times delta t is equal to our change in momentum. And that is the impulse momentum theorem. Pretty awesome if you ask me. Another way we can say this is whenever an impulse is applied to an object, we can change its momentum. So anytime we have a force, an outside force acting upon our object, we change the momentum of that object. So here we have a question. A light plastic cart and a very heavy steel cart are both pushed with the same force for 1 second, starting from rest. After the force is removed, the momentum of the light plastic cart is blank compared to that of the heavy steel cart. So go ahead and choose your answer. In this case, it is equal to. And the reason we know that the momentum is equal to is because we have the same force applied over the same time, which means both carts experience the exact same impulse. Because of that, they experience the exact same change in momentum. So we know that they have the same change in momentum, which is going to be equal to PF minus PO. And because our initial momentum is 0, that means our change in momentum is equal to our final momentum in this case. And because the change in momentum is the same, the final momentum is also the same. So momentum and impulse. So the rate of change in momentum is equal to the net force applied to it. A way to say that is just delta P over delta T is equal to our average force. The more momentum an object has, the harder it is to stop. The more force you would need to stop that object. Or you would need to extend the change in momentum. So if you increase the time it took, the time that you applied that force to change the momentum, you would use a lower force. So whenever you jump off off something high, why is it better to bend your knees? Well, when you bend your knees, you're extending that time. And so the change in momentum is the same, but the force you feel is going to be smaller than if you just, locked your knees. Because when you lock your knees, delta T is really, really small, but change in momentum is the same. So you have a very, very large force. Whereas when you bend your knees, you still have that same change of momentum because you're going from whatever velocity is to 0. However, your change in time is much larger, so the average force on your knees is going to be smaller. So I have a question here. A 50-gram golf ball leaves the face of the club at 20 meters per second. If the club is in contact for 0.002 seconds, what is the average force acting on the ball? Well, in this case, we know what the mass is, and we know what the initial velocity is. We also know what delta T is, and we know what our final velocity is, which is pretty cool. So in this case, we're going to use our impulse momentum theorem, and we know that that force times our change in time is equal to our mass times our velocity minus our mass times our velocity. So if we want to just find out what that force is, we know that that force is just going to be equal to our change in momentum over our change in time. We can go ahead and solve, and we find that our average force is going to be equal to 500 newtons. So that the average force that the golf club that the golf ball applies on our, or the golf club applies on our golf ball is going to be right around 500 newtons. Another question. A 500-gram ball moves to the left at 20 meters per second, striking a bat. The ball leaves in the opposite direction at 40 meters per second. What was the impulse? Well, we know what our mass and velocity is, and we know what our change in time. We do not know what our change in time is. So what is the impulse? Come on. So we know that impulse is equal to our change in momentum. We know what our final and initial velocities are. All we have to do is plug into this impulse momentum theorem, and we find out that our impulse is going to be 30 newton seconds, or if you wanted to, you could write it as 30 kilogram meters per second, if they are the exact same thing. So, you awake in the night to find that your living room is on fire. Your one chance to save yourself is to throw something that will hit the back of your bedroom door and close it, giving you a few seconds to escape out the window. You happen to have both a sticky ball of clay and a super bouncy super ball next to your bed, both the same size and the same mass. You've only had time to throw one ball. Which will it be? Your life depends on making the right choice. We are going to go over this in class tomorrow. That is all I have to say about momentum for now. I look forward to seeing you.